Welcome to this explainer. Look, if you're currently right in the middle of a brutal study session, or maybe you're just wrapping up a completely chaotic week of classes, I want you to just take a deep breath. Seriously, settle in. Today, we're going to take a really calm, relaxed look at something so incredibly ordinary, you probably see it every single day without giving it a second thought. And that is boiling water. We're going to explore the quiet, invisible stresses hidden inside this super simple process, and how understanding them can actually teach us a lot about managing pressure, not just in massive industrial machines, but, maybe even a little bit in ourselves. Think about that cheap plastic or metal electric kettle sitting in your dorm room or apartment right now. Have you ever looked inside and noticed this layer of chalky white buildup coating the bottom? It's a pretty low-stakes annoyance, right? You might scrub it out with some vinegar every few months, or, let's be honest, maybe you just completely ignore it. That white stuff is simply the dissolved calcium and magnesium salts that the water naturally leaves behind when it turns into steam. In your kitchen, it's just a minor inconvenience. Okay, let's dive into this, because when we take that exact same, highly relatable concept and scale it up to the size of a massive power plant boiler, the stakes change absolutely dramatically. In an industrial boiler, water is heated under immense pressure to generate steam for electricity or heavy manufacturing. We're talking millions of gallons of water continuously evaporating. And just like your kettle, when that water boils, it leaves its chemical baggage behind. But on this scale, that quiet accumulation of impurities doesn't just look messy. It leads to choked pipes, warped metal, catastrophic failure, and honestly, even massive explosions. So let's break down the first major issue: soft sludges and hard scales, or what we can think of as the heavy buildup. When water is put under that kind of intense heat and pressure, its impurities form two totally distinct types of heavy buildup. First up, we have sludge. Think of sludge as the softer, sort of lazier byproduct. As the boiler water gets more and more concentrated with salts, things like magnesium carbonate or calcium chloride, these impurities hit their saturation point and just drop out of the water. They form this loose, soft, almost silky or slimy precipitate that's suspended in the liquid. And because these particular salts are actually less soluble in cold water than in hot water, they tend to just quietly drift and gather in the colder, slower-moving parts of the boiler, like the pipe connections. Now, what's really interesting about this slide is the complete contrast here. This right here is scale. While sludge is soft and loose, scale is this terribly stubborn, hard, super adherent coating that literally bakes firmly onto the inner walls. It's formed by substances like calcium sulfate and silica, which actually become less soluble as the temperature skyrockets. So instead of drifting around, they precipitate directly onto the absolute hottest surfaces of the boiler plate. To put it simply, sludge chokes the flow, but scale suffocates the metal. Sludge can definitely clog up your pipes and lower your boiler's efficiency, for sure. But scale is far more dangerous. It acts as a thermal insulator. It completely prevents the heat of the furnace from passing safely into the water. So, because that intense heat can't escape into the water, the metal boiler wall underneath the scale just overheats. It expands unevenly, then the brittle scale cracks, and suddenly, relatively cool water rushes right into that crack, hitting the superheated glowing iron plate. It instantly flashes into a massive volume of steam, creating a sudden, violent spike in pressure that can literally burst the boiler apart. Moving up from the bottom, let's look at bubbles, priming, and foaming. This is where we examine the chaotic surface. So that heavy buildup is the danger lurking at the bottom of the boiler. But up at the very top, impurities actually change the physical tension of the boiling water itself. Ideally, you want a boiler to produce pure, completely dry steam, but sometimes it produces what engineers call carryover or wet steam. This happens when the evaporating steam inadvertently grabs onto and carries droplets of unevaporated liquid water, along with all their dissolved salts, straight out of the boiler and into the delicate downstream machinery. This wet steam is a massive headache. It drastically lowers energy efficiency, and when that steam finally dries out later in the turbines, it drops those hard salt crystals right onto the high-speed turbine blades, severely degrading them over time. Carryover usually happens in one of two ways: priming or foaming. Priming is just pure chaos. It's the violent splashing of large drops of water right up into the steam outlet, usually caused by a poor boiler design or steam moving at ridiculously high velocities. Foaming, on the other hand, is completely a chemical issue. If the water happens to contain oils, fats, or certain alkalis, those impurities actually lower the surface tension of the water. They collect around the steam bubbles, creating this tough, persistent layer of foam on the surface that simply refuses to pop. Now, let's go even deeper and explore the quiet stress of the metal itself, corrosion and embrittlement. We've talked about the visible buildups, and we've talked about the chaotic bubbles, but the most insidious danger is entirely invisible. Let's move to this and see how it builds. It's a phenomenon known as caustic embrittlement. It honestly reads almost like a slow-motion tragedy. Step 1. In these high-pressure boilers, leftover sodium carbonate from earlier water softening treatments gets hydrolyzed into sodium hydroxide, which is caustic soda. This highly alkaline water quietly sneaks into microscopic, hair-thin cracks in the boiler's riveted joints through capillary action. Step 2. Because the metal is blazing hot, the water inside that tiny crack evaporates, leaving the caustic soda behind. This cycle just repeats and repeats until the chemical is incredibly concentrated. Step 3. This hyperconcentrated caustic soda begins to actively attack the iron, specifically targeting the areas where the metal is already under physical stress from being bent or riveted into place. And this brilliantly illustrates exactly how that plays out. Because the iron right at the rivet is under so much physical stress, its atoms are actually at a higher energy state. This effectively turns the boiler itself into a tiny battery, an electrochemical concentration cell. The stressed iron at the rivet acts as the anode, and the unstressed flat boiler plate acts as the cathode. The metal literally sacrifices itself, dissolving away as sodium ferrochlorate. The iron slowly becomes completely brittle, and eventually the joint just snaps. And, it's not just caustic soda we have to worry about here. Even invisible, naturally dissolved gases carry their own quiet stress. Dissolved oxygen in the feed water will directly attack the iron to produce rust. Dissolved carbon dioxide reacts with the water to form carbonic acid, which drops the pH and leads to acidic corrosion, leaving these rough, pitted scars across the metal surface. If left unchecked, these incredibly quiet chemical reactions will easily eat right through the strongest steel. Which brings us to a much more peaceful final takeaway: softening the flow. Now, while all of this sounds super intense and catastrophic, engineers actually care for these highly stressed machines using some really elegant, relatively simple chemical solutions. We don't just sit back and let the machines destroy themselves, we soften the flow. To keep the boiler running smoothly, the water is treated before and during its time in the system. Engineers use internal treatments like Calgon, that's sodium hexametaphosphate, which beautifully wraps up the scale-forming impurities into these harmless, highly soluble complexes, so they literally can't stick to the walls. We perform regular blowdown operations, gently drawing off the water from the bottom to release all that accumulated soft sludge before it can cause a blockage. And we carefully monitor the pH, neutralizing the acids and alkalis so the metal can exist in a stable, balanced environment. So the crucial point I want you to take away is this. What's true for the industrial boiler is actually surprisingly true for us too. As a student, you're constantly under high pressure, and it is so incredibly easy for daily stressors to slowly concentrate in the cracks until you start to feel brittle. But remember, even the absolute strongest metals crack under concentrated stress. We have to do our own internal maintenance. We have to soften our reactions to the baggage of the day, perform our own mental blowdowns to vent the built-up sludge, and neutralize the pressure before we overheat. So as you head back to your studies today, I just want you to ask yourself, what exactly is your internal blowdown valve, and when are you going to use it? Thanks so much for joining me on this explainer today. Take care of yourselves.